I'm sure everyone has heard of carbon dioxide and its role in climate change. What you may not have heard of is nitrous oxide, a far more powerful greenhouse gas. Over 100 years, 1 pound of nitrous oxide in our atmosphere has the same warming effect as 300 pounds of carbon dioxide. 40% of all nitrous oxide emitted comes from human activities, and of this, approximately 3/4 comes from our management of agricultural soils. Unfortunately, a key word there is approximately. Our estimates of our largest source of nitrous oxide still have numerous uncertainties, and one of the largest of which is the amount emitted from nitrogen fertilizers. Though its use is crucial in helping farmers meet our ever-growing needs, often less than half of the nitrogen in fertilizers is ever absorbed and utilized by the crop. Instead, this nitrogen is lost to the surrounding environment, and exactly how much of it is lost as nitrous oxide is a source of uncertainty. While there have been several key studies examining such losses, many have used traditional field plots open to the surrounding environment, where nitrogen can easily escape our measurements. When this happens, it becomes difficult to obtain a complete picture of where all the applied nitrogen went, and it reduces our ability to detect how subtle changes in fertilizer application impact important losses such as nitrous oxide. My research uses an innovative field study design whereby massive blocks of soil are enclosed on the side and on the bottom with steel. To the bottom of every soil block is a single pipe that collects all excess water and nitrogen that would be normally lost in an open field design. This enables me to precisely measure nitrogen losses. Using this design over the last 3 years, I've taken numerous measurements, including nitrous oxide emitted, nitrate leached, and the nitrogen removed in harvest, all to put nitrous oxide into the context of how nitrogen moves through the crop system. So far, I have found 2 exciting things. First, I have found that my measurements differ markedly from large-scale predictions. In fact, my measurements were sometimes twice as large as that predicted. This means in some regions of the U.S. Corn Belt, we could be grossly underestimating our actual nitrous oxide emissions when using popular methods for predictions. Fortunately, the second thing I have found is that subtle reductions in our fertilizer application have a disproportionate effect on our nitrogen losses. So even small reductions in our fertilizer applications can sometimes result in a larger reduction of our losses than what we may expect. Equipped with these 2 insights, I hope to help many better understand what role our crucial fertilizer applications have in climate change and what we may do to properly address it. Thank you.